York State Building Code requires the grounding electrode conductor, also known as the GEC, to loop through the rods and back to the panel for all services. This includes services for detached structures. This requirement can be found in Section 230.92 of the NYC. Section 230.92 states the grounding electrode conductor shall be run to each grounding electrode and back to the panel where it shall be connected to the grounded neutral conductor. Now let's talk about supplemental ground rods and water supplies. The belief that only one supplemental rod is required where city or municipal water is provided is not a New York State amendment to the National Electrical Code. It is a common misconception that is likely based on the fact that the NEC does not explicitly require two supplemental rods for systems that are connected to a city or municipal water supply. However, the NEC does require two supplemental rods for systems that are not connected to a city or municipal water supply, and it does not make any exceptions for systems that are connected to other types of water supplies, such as private wells. The reason for this requirement is that the NEC considers city or municipal water supplies to be a reliable source of grounding, while private wells are not. This is because city or municipal water supplies are typically connected to a metal water main that is buried underground, which provides a good path to ground. Private wells, on the other hand, are typically connected to a plastic pipe that is not buried underground, which does not provide a good path to ground. Therefore, if you are installing a grounding system for a system that is not connected to a city or municipal water supply, you must install two supplemental rods. When installing grounding electrodes, understanding the NEC is crucial. Section 250.53. It details the requirements for rod, pipe, and plate electrodes. These electrodes must contact the earth directly. The installation of ground rods, for instance, mandates that they be driven to a depth of at least 8 feet or 2.44 meters. The upper end must be below the surface unless protected or driven at an angle not exceeding 45 degrees from vertical. The NEC allows the use of a single ground rod if its resistance to ground is 25 ohms or less. If it exceeds this value, a second ground rod is required. The two ground rods should be separated by a minimum of 6 feet or 1.83 meters to ensure they tap into different areas of the earth. Now let's discuss the grounding electrode conductor. It connects the equipment grounding system and the grounded conductor at the service equipment to the grounding electrode. The size of the grounding electrode conductor is determined by NEC Table 250.66 based on the size of the service entrance conductors. The grounding electrode conductor can be made of copper, aluminum, or copper-clad aluminum and must be protected from physical damage. The connection to the grounding electrode must be made using listed connectors or clamps suitable for the purpose. The NEC also addresses the use of metal water pipes as grounding electrodes in Section 250.52. A1. A metal underground water pipe in direct contact with the earth for 10 feet or 3.5 meters or more can serve as a grounding electrode. It must be supplemented by an additional electrode, such as a ground rod or ground ring. The connection to the water pipe must be made within 5 feet or 1.52 meters of its point of entrance to the building. This connection minimizes the potential for voltage differences between the pipe and other grounded metal parts in the building. Ground rings, as described in NEC Section 250.52. A4 consist of a bare copper conductor no smaller than 2 American wire gauge that is buried in the earth encircling the building or structure. The ground ring must be buried at a depth of at least 2.5 feet or 762 millimeters. It must be at least 20 feet or 6.1 meters in length. Concrete encased electrodes, also known as UFA are covered in NEC Section 250.52. A3. These electrodes consist of at least 20 feet or 6.1 meters of bare copper conductor no smaller than 4 American wire gauge that is encased in concrete. The concrete must be in direct contact with the earth. These electrodes are typically installed in the footings or foundations of buildings. The selection of the appropriate grounding electrode depends on various factors including soil conditions, local codes, and the availability of suitable electrodes. Soil resistivity is a crucial factor in determining the effectiveness of a grounding system. High soil resistivity makes it difficult to establish a low impedance path to ground. Soil resistivity can be improved by treating the soil with ground-enhancing materials. These materials help to reduce the resistance between the grounding electrode and the surrounding earth. Ground testing is essential to verify the effectiveness of a grounding system. A ground resistance tester measures the resistance of the grounding electrode to ground. The test results should be compared to the requirements of the NEC and local codes. Regular ground testing is recommended to ensure that the grounding system continues to provide adequate protection. Improper grounding can lead to electrical shock hazards, equipment damage, and fire. Grounding provides a low impedance path for fault currents to flow back to the source, tripping the overcurrent protective device and disconnecting the circuit. Grounding also helps to reduce voltage differences between metal parts, minimizing the risk of electrical shock. Bonding is another important aspect of electrical safety. Bonding connects metal parts together to create a common ground potential. Bonding helps to prevent voltage differences between metal parts, reducing the risk of electrical shock. The NEC requires bonding of metal water pipes, gas pipes, and other metal parts that are likely to become energized. Equipment grounding conductors provide a path for fault current to flow back to the source. Equipment grounding conductors must be sized according to NEC Table 250.122 based on the size of the overcurrent protective device protecting the circuit. Equipment grounding conductors can be installed in the same raceway or cable as the circuit conductors, or they can be installed separately. Ground fault circuit interrupters, also known as GFCIs, are devices that protect people from electrical shock. GFCIs monitor the current flowing in a circuit and detect any imbalance between the hot and neutral conductors. If an imbalance is detected, the GFCI quickly trips the circuit, cutting off the power and preventing electrical shock. GFCIs are required in many locations, including bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, also known as FSIs, are devices that protect against electrical fires. FSIs detect arc faults, which are dangerous electrical discharges that can cause fires. When an arc fault is detected, the FSI trips the circuit, cutting off the power and preventing a fire. FSIs are required in many locations, including bedrooms and living rooms. Surge protective devices, also known as SPD, protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power grid switching, and other events. SPD divert the surge current to ground, protecting sensitive electronic equipment from damage. SPD are recommended for homes and businesses to protect valuable electronic equipment. Electrical inspections are important to ensure that electrical systems are installed and maintained in accordance with the NEC and local codes. Electrical inspectors check for compliance with safety regulations and identify any potential hazards. Regular electrical inspections can help to prevent electrical shocks, fires, and other electrical accidents. The National Electrical Code is a comprehensive set of standards for electrical safety. The NEC is updated every 3 years to reflect the latest advances in electrical technology and safety practices. It is important for electricians, contractors, and homeowners to stay up to date on the latest requirements of the NEC. Electrical safety training is essential for anyone who works with electricity. Electrical safety training teaches workers how to identify electrical hazards, how to work safely around electricity, and how to respond to electrical emergencies. Proper electrical safety training can help to prevent electrical shocks, fires, and other electrical accidents. Remember that compliance with the NEC and local codes is essential for electrical safety. When in doubt, consult with a qualified electrician or electrical inspector. Always prioritize safety when working with electricity. It is also important to remember that electrical codes and regulations can vary depending on the location. Always check with the local authorities to ensure that you are following the correct electrical codes for your area. Proper maintenance of electrical systems is also crucial for electrical safety. Regularly inspect electrical wiring, outlets, and appliances for any signs of damage or wear. Replace any damaged or worn electrical components immediately. Keep electrical panels and equipment clean and free of obstructions. Avoid overloading electrical circuits, as this can lead to overheating and fires. Use extension cords sparingly and never run them under rugs or furniture. By following these electrical safety tips, you can help to protect yourself, your family, and your property from electrical hazards. The purpose of grounding is to provide a low impedance path for fault current to return to the source, which allows the overcurrent protection device to quickly clear the fault. This protects people from electrical shock hazards. Grounding also helps to stabilize voltage and reduce electrical noise. The grounding electrode system must be properly installed and maintained to be effective. Proper grounding can help prevent fires. Electrical fires are often caused by faulty wiring or overloaded circuits. Grounding helps to prevent these fires by providing a path for fault current to flow back to the source, which trips the overcurrent protection device. Proper grounding protects sensitive electronic equipment from damage. Voltage surges can damage sensitive electronic equipment, such as computers, televisions, and other electronic devices. Grounding helps to protect this equipment by diverting the surge current to ground. Grounding provides a safer electrical environment for everyone. By following the NYCBC and local codes, and by taking proper electrical safety precautions, you can help to create a safer electrical environment for yourself, your family, and your community. Remember, working with electricity can be dangerous. Always consult with a qualified electrician if you have any questions or concerns about electrical safety. The grounding electrode conductor must be continuous and unbroken. Splices are not permitted in the grounding electrode conductor. The grounding electrode conductor must be securely connected to the grounding electrode into the service equipment. The grounding electrode conductor must be protected from physical damage. The grounding electrode system must be accessible for inspection and testing. The grounding electrode system must be kept free of corrosion. The grounding electrode system must be properly maintained. The grounding electrode system should be tested regularly to ensure that it is functioning properly. If the grounding electrode system is not functioning properly, it should be repaired or replaced. If you have any questions or concerns about your grounding system, you should consult with a qualified electrician. A proper grounding system is an important safety feature in any electrical system. It protects people from electrical shock hazards, helps to prevent fires, protects sensitive electronic equipment from damage, and provides a safer electrical environment for everyone. Proper grounding is not just about following the code. It's about understanding the principles behind it and applying them to create a safe and reliable electrical system. That includes selecting the right grounding electrodes, sizing the grounding electrode conductor correctly, and making sure that all connections are tight and secure. It also means understanding the role of bonding and how it contributes to overall electrical safety. By paying attention to these details, you can ensure that your grounding system is providing the protection it's designed to offer. Another important aspect of grounding is documentation. Keep records of all grounding system components, including the type of grounding electrodes used, the size of the grounding electrode conductor, and the results of ground resistance tests. This documentation can be helpful for future inspections and maintenance. Also, it's crucial to consider the specific requirements of the equipment being grounded. Some equipment may require special grounding provisions, such as isolated grounding systems. Make sure to consult the manufacturer's instructions and the NYCBC for any specific grounding requirements. Proper grounding is a continuous process. It's not just something that's done during the initial installation. Regular inspections and maintenance are necessary to ensure that the grounding system continues to function properly over time.